Welcome, my dear student. Myself, GEOMETRY-UNIT1, Assistant Professor, Department of Mathematics, St. Joseph College of Arts and Sciences, Kadal. This is a differential geometry video, Unit 1, Part 5. Already we've seen Part 1 and Part 2, basic concept of differential geometry or length in differential geometry, some problems based on Part 2. And third and fourth video, we discussed about the unit tangent vector, rectifying plane, normal plane, and Sjctnc-Differential formula, and finally curvature and dashing. So this is the video for it. To finding the formula for the curvature and dashing, problems in curvature and dashing, equation for oscillating circle, and equation for oscillating sphere. So now we're going to find the equation for curvature and dashing. So it is a curvature and dashing having the two parameter, one is S, another one is U. So now we're going to see one by one. So we well known that R vector dash equal to T vector. So now we're going to differentiate the equation with respect to S. So we will get R vector double dash equal to T R vector dash by T S. So that is R vector double dash is equal to T dash. By the Sjctnc-Differential formula, we know that T dash equal to kappa n. So therefore we may write T dash, that is R double dash equal to kappa n. So now we are taking the cross product between R vector dash and R vector double dash. So that is equal to T vector cross kappa into n. So kappa is a constant we take outside, therefore R vector dash plus R vector double dash equal to kappa into V vector. So now we are taking the modulus. So therefore we write that mod R vector dash plus R vector double dash equal to kappa into mod V. But it is a unit vector, so therefore mod V is 1. So we simply write kappa. So from this equation, we say immediately the curvature kappa equal to the R mod R vector dash plus R vector dash. It is an equation for curvature with the parameter S. So now next we are going to find the Gaussian parameters. So we know one of this equation from this unit, the box product R vector dash comma R vector double dash R vector triple dash equal to kappa square tau. This is the equation from the oscillating plane, already we seen there in video 3. So from this one, tau equal to box product of R dash R double dash R triple dash divided by kappa square. So this is the kappa, we substitute instead of here, so we can get tau equal to the box product R dash R double dash R triple dash divided by mod R vector dash plus R vector double dash the whole square. So now we are going to find the curvature and dashing in terms of the parameter U. That is, we are using the notation dot here. So therefore R vector dot is equal to dr by du. Now we change this one as independent of S. Therefore dr by ds into ds by du. That is equal to R vector dash into S dot, because the first one is differentiation with respect to S. So we are using notation as dash. Second one is differentiation with respect to U. Therefore we are using notation as dot. So therefore R vector dash dot S dot. Similarly, we can find differentiation with respect to U. We get R vector double dot equal to kappa S dot square n cap plus S double dot t cap. So now again taking this cross product between this equation R vector dot and R vector double dot. So it will be equal to kappa S dot q into V vector. So we are taking modulus, we will get mod R vector plus R vector double dot equal to kappa S dot q. So from this one, we can say immediately kappa equal to mod R vector plus R vector double dot divided by S dot. And already we know in video 3, one of the most important equation from the oscillating plane, the box product R vector dash R vector double dash R vector triple dash equal to U dash power 6 into box product R dot R double dot R triple dot. So now we simplify this one. We replace this U dash as 1 by ds by du whole power 6. So which is equal to kappa square tau into the box product of R dot R double dot and R triple dot divided by S dot power 6. We need tau. So therefore tau equal to 1 by s dot over 6 into, we know value of kappa from this above equation. Now we substitute here. Therefore it is a box product of r dot comma r double dot comma r triple dot divided by mod r vector dot plus r vector double dot divided by s dot cube the whole square. So we are squaring, we get the modulus of square divided by s dot over 6. So therefore s dot over 6 will be cancelled. The tau equal to box product of r vector dot comma r vector double dot comma r vector triple dot divided by modulus r vector dot plus r vector double dot the whole square. So now we are going to find some problems using curvature and dash. So given r vector is given, r vector equal to u comma u square comma u cube. We need a curvature means this is in parameter with respect to u. So we are using the second formula. So now we are going to differentiate the term r dot. So 1 comma 2u comma 3u square, r double dot 0 to 6u and r triple dot 0 0 comma 6. So we know the formula for curvature, kappa equal to the box for mod r vector dot cross r vector double dot divided by s dot over 3. So we need a cross product of r vector cross r double dot. So by the formula we are using ijk, first r vector dot component, second r vector double dot component. So after expansion this matrix, we will get the value 6u square I vector minus 6u j vector plus 2k. So we need the modulus means we are taking the square root and squaring the components of each vector, coefficient of each vector. So therefore we will get 2 into square root of 9u power 4 plus 9u square plus 1. So we know that s dot equal to mod r vector dot. R vector is x dot square plus y dot square plus z dot square. So therefore s dot equal to 9u power 4 plus 9u square plus 1 whole power 1 by 2. S dot cube means whole power 3 by 2. So therefore kappa equal to, we are substituting the r vector cross r vector double dot value and the s dot cube value. So therefore we can get kappa equal to 2 into the square root of 9u power 4 plus 9u square plus 1 divided by 9u power 4 plus 9u square plus 1 whole power 3 by 2. Similarly, we find that tau equal to box product of r dot, r double dot and r triple dot divided by mod r vector dot plus r vector double dot the whole square. Already we know what is the mod r vector dot plus r vector double dot. So we find the box product. So box product means modulus. So therefore we expand this matrix and we get the value is 12. So therefore tau equal to 3 by 9u power 4 plus 9u square plus 1. So now we are going to see oscillating circle. What is oscillating circle? The oscillating circle at a point P on a curve is a circle which has the 3-point contact with the curve at P. That oscillating circle lies on the oscillating plane at P. Now let us see this figure, the xy component. We are in this component, we are taking a curve AB. So that curve can be drawn a unit tangent line P and passes through the point P. From this point P, we can draw the curve. It will form some curve. We can draw the line segment from P. So it forms some curve. The curve will be called 3-point contact. We will call it as a oscillating circle. Now let us see in video form. This is the curve because we are taking the curve, the point moving, and it will be gives the such curve, and it shows that it forms looks like this. So which is called an oscillating circle. So now we are going to find the equation of the oscillating circle. So let us see this figure. We are taking the curve from this position vector. We are using the curve, and from this one we can draw the line segment from this one. So let us see which is a curve C. So from this one we write that EC vector equal to O into N. From the vector additive law, you may write this one. PC vector is OC vector minus OP vector equal to rho into n cap. Rho is the radius. Okay. C minus R vector equal to rho into n cap. So this is the equation for oscillating circle. So now we are going to derive one of this result is equation for oscillating circle at the point P on the curve. Is we know that C vector minus R vector equal to rho into n cap from the previous. Now we are taking dot product itself. Therefore C vector minus R vector dot C vector minus R vector equal to rho into n cap dot rho into n cap. So this is equal to rho square into n dot n value is 1. So this is the equation as C vector minus R vector whole square equal to rho square. Let the curve be the parameterized with respect to the arc length. So let's choose f of s is equal to, we are changing this form as r C vector minus R vector whole square minus R square. So oscillating circle means it is 3-point contact. 3-point contact means that is f triple dash is exist. So before this point will be 0. That is f dash and f double dash equal to 0. So therefore we will consider f equal to 0. F is, we know this previous equation, C vector minus R vector whole square minus R square. So that is equal to 0. From this equation we will get C vector minus R vector dot C vector minus R vector equal to R square. So now we are going to differentiate this equation with respect to s. So we will get minus T vector dot C vector minus R vector plus C vector minus R vector dot minus T vector. R vector is 0. So we know the dot product A dot B equal to B dot A. So therefore we may write this one is 2 times C vector minus R vector dot minus T vector equal to 0. So which is equal to C vector minus R vector dot T vector equal to 0. Again we will differentiate with respect to s from this above equation. We will get minus T vector, that is R, C vector is 0, R dash is, we will write T vector dot T vector plus C minus R into T dash equal to 0. So T dot T value is 1, so minus 1 plus kappa into C vector minus R vector dot n cap. Kappa is constant, we take outside. So minus 1 plus kappa into C minus R is like this equation 1, we will know the equation of oscillating plane C minus R vector equal to rho into n cap. So that is rho is constant, we will take outside, therefore minus 1 plus kappa rho, n dot n value is 1. So therefore kappa into rho equal to 0. It is kappa rho equal to 1. So from this one, we write rho equal to 1 by kappa. And mod rho equal to kappa units. That rho is called the radius of the curvature at the point. It is a very important result for this one. In the future, suppose if you attempt any competitive exam, maybe accept a question from this one, what is the radius of curvature and PGT or something like it. Okay. So the center of the curvature is center of the oscillating circle whose position vector is given by, we may write this one that C vector is equal to R vector plus O into n cap. Similarly, the radius of the torsion is tau equal to sigma equal to 1 by tau. Because sigma equal to tau inverse. And next one is that oscillating sphere. The oscillating sphere at a point P on a curve is the sphere which has the 4-point contact with the curve at the P. Already we see what is the oscillating circle. So it will become from some spherical curvature form. We call it an oscillating sphere. The equation of the oscillating sphere at a point P on the curve, we may write this one as the C vector equal to position of the vector of the center of the oscillating sphere. R is radius, R vector is the position of the vector at the point P. So we may write this one as C vector minus R vector equal to R square. So using this one, are we going to find some result? The equation of the oscillating sphere at the point P is C vector minus R vector whole square equal to R square. So that is the, we choose the parameterized equation general form f of s equal to C vector minus R vector minus R square. It is a 4-point contact up to the f triple dash equal to 0. So therefore f equal to 0, f dash equal to 0 and f double dash equal to 0, f triple dash equal to 0. So therefore f equal to 0 means we may write by the chance of the oscillating circle way. So again it will be the same result for it. C vector dot C vector minus C vector dot C vector equal to R square. Again we will differentiate with respect to S. We will get the values 2 times C vector minus R vector dot minus T equal to 0. So that is C vector minus R vector into T vector equal to 0. So again differentiate with respect to S, we will get the values C vector minus R vector as that is C vector differentiation 0, R vector is R dash dot T plus C vector minus R vector dot T vector differentiation is T dash. So it is R vector means T vector, therefore minus T dot T, C vector minus R dot T dash value by the Sjctnc-Differential formula we may write kappa n, therefore minus 1 plus T dot T value is minus 1, therefore minus 1 plus C vector minus R vector dot kappa n equal to 0, that is C vector minus R vector dot kappa n equal to 1. We need the value kappa is shifted to this right hand side, therefore 1 by kappa. By the radius of the oscillating sphere we know it, one oscillating circle we know it, radius of rho equal to 1 by kappa. So therefore we may write C vector minus R vector dot n cap equal to rho. So again we will differentiate with respect to this S. So we will get minus T vector dot n cap plus C vector minus R vector dot n dash by again with the Sjctnc-Differential formula we may write tau b minus kappa t equal to rho dash. So the T dot n, A dot b value is 0, like the T dot n equal to 0, C vector minus R vector dot tau b minus C vector R vector dot kappa t. We are multiplying or taking dot product with the inner and it is equal to again rho dash. So from this one we take outside C vector minus R vector dot B vector minus second one is kappa is constant, we take outside C vector minus R vector dot T vector equal to rho dash. So that is a vector. The second one already we know it is a 0 by equation 2. So therefore we may write tau into C vector minus R vector dot B vector equal to rho dash. So C vector minus R vector dot B cap equal to rho dash by tau. Tau is already we know 1 by sigma, so therefore 1 by tau is sigma. So therefore C vector minus R vector dot B dash equal to rho dash into sigma. So that is we write clearly we know by this oscillating from this equation C vector minus R vector is possibly write lambda n plus mu p. That is a normal and a binormal plane with a constant multiplication. So therefore we are write this one taking dot product with itself this equation 5 with n. So C vector minus R vector dot n cap equal to lambda into n cap dot n cap plus mu into B vector dot n cap. So this is clearly shows that C vector dot R vector dot n cap equal to lambda if you are taking the dot product with the n, and if you are taking dot product with the B from this equation by 5, so you get the equation as C vector minus R vector dot B vector equal to B. So now we compare this equation with 3 and 4, we will get the value lambda equal to rho and mu equal to B dash sigma. So therefore we will write this equation 5 as C vector minus R vector equal to rho into n cap plus rho dash into sigma b. That is the center of the spectral curvature is the center of the oscillating sphere and its position vector is given by, we may write again that is C minus R equal to rho n plus lambda mu b. So that is we write C vector equal to R vector plus rho n plus rho dash into sigma b. So again by choosing this equation 6, C vector minus R vector dot C vector minus R vector equal to again rho n plus rho dash sigma b dot rho n plus rho dash sigma b. So that is we write this one as C vector minus R vector whole square equal to rho square plus sigma square rho dash square. So this is already we know by the equation of static sphere, it is r square. So that is equal to rho square plus sigma square in the rho dash square. So that is r equal to rho square plus sigma square rho dash square whole power 1 by 2. So which is the radius of the spherical curvature? The radius of the spherical curvature is rho square plus sigma square rho dash square whole power 1 by 2. So the center at a point P on the curve is C vector is equal to R vector plus rho n. The center of the spherical curvature at the point is C vector equal to R vector plus rho n cap plus rho dash sigma. When kappa is constant, we may write rho equal to 1 by kappa, rho dash is equal to 0. That is, we will see from this above equation, it is we conclude that the center of the curvature is equal to center of the spherical curvature and radius of this curvature is equal to radius of the spherical curvature. Thank you.